There's a hole in space big enough to swallow 1 billion solar systems. No stars, no galaxies, almost nothing. And astronomers found it by accident. We'll go inside the void that broke our best models of the universe. We'll discover the emptiness surrounding our own Milky Way. And we'll hit the moment scientists realized the cosmos plays by rules we haven't figured out yet. If you enjoy the ride, a like and subscribe keeps this going. Let's go. The year is 1981. A team of astronomers is building a map of the universe, and something is very wrong. Robert Kirshner and his colleagues at the University of Michigan were doing something most scientists considered routine. They were measuring the distances to galaxies across a wide slice of sky. The goal was simple: plot where everything sits, build a three-dimensional picture of the cosmos, and confirm what everyone expected to find: a roughly even spread of galaxies in every direction. Maybe some clumps here and there, nothing shocking. Then they pointed their telescopes toward a region of sky marked by the constellation Boets, the herdsman, and found almost nothing. Not a gap, not a thin patch. A genuinely enormous stretch of space with almost zero galaxies inside it. The team stared at their data, they checked their instruments, they ran the numbers again. The equipment was fine, the data was clean, the emptiness was real. Kirshner called it the Great Nothing. Astronomers expected to find roughly 2,000 galaxies in a region that size, a busy, crowded stretch of cosmic real estate, packed with light and matter the way every other part of the sky seemed to be. Instead, they counted 60. 60 galaxies in a space so vast it takes light 330 million years just to cross it from one side to the other. To picture that distance, imagine the entire Milky Way, a galaxy so wide that light takes 100,000 years just to cross it. Now, stack copies of the Milky Way end to end, over and over, for 330 million light years. The Boetis void swallows all of that space and fills it with almost nothing. The team published their findings, the scientific community paid attention, and then the questions started. How does something that empty exist? Under standard physics, the universe formed from a hot, dense state after the Big Bang. Matter spread outward, cooled, and slowly clumped together under gravity. That process creates structure, threads of galaxies, walls of galaxy clusters, and smaller gaps between them. Scientists expected voids, small ones, maybe a few tens of millions of light years across. Manageable sizes that fit neatly inside their models. 330 million light years does not fit neatly inside any model. For a void that large to form by gravity alone, the universe would need far more time than it has had. The math doesn't close. Standard physics looks at the Boötes void and produces no clean answer. And here is where it gets stranger. When astronomers looked more carefully at the 60 galaxies sitting inside the void, they found something unexpected. Those galaxies were arranged in a loose, tube-like chain running through the center of the empty region. They were not scattered randomly the way you'd expect, if they just happened to be left behind. They were lined up, connected by faint threads of gas, like beads on a nearly invisible string, stretched across a 330 million light-year canyon. Nobody fully understands why. One early theory suggested the Boötes void might actually be several smaller voids that merged together over billions of years, creating one massive hole. But that explanation only pushes the problem back a step. Standard gravity still struggles to explain how even smaller voids merged that fast. Kirshner's team had found something that shouldn't be there. A hole in the universe so big, it challenged the rules of how the universe builds itself. But the Boötes void, enormous as it is, would eventually stop being the most troubling void astronomers knew about. Something far larger was waiting, and it was a lot closer to home. Zoom out far enough, and the universe stops looking like a collection of stars. From a great enough distance, galaxies become tiny dots. Then those dots reveal a pattern. They cluster along thin, curving threads, like foam clinging to the surface of an invisible ocean. Between those threads, enormous gaps open up. Empty bubbles of space separated by walls of light and matter. Scientists call this the cosmic web, The cosmic web is the largest confirmed structure in the observable universe. It is made of three main parts: filaments, which are the long threads of galaxies and gas connecting everything together; walls, which are flat sheets where filaments meet; and clusters, which are the dense, bright knots sitting at the intersections. The gaps between all of that are the voids. Here is what makes it strange. Those voids take up roughly 80% of the observable universe's total volume. 80%, the threads, walls, and clusters that hold nearly all the matter in existence, are packed into the remaining 20%. The cosmos is mostly made of almost nothing, and the something is squeezed into thin lines and sheets running between the emptiness. How did this pattern form? Scientists believe it started before any stars existed. In the earliest moments after the Big Bang, the universe was a hot, nearly uniform cloud of energy and matter. Nearly uniform, but not perfectly. Tiny random fluctuations created spots that were ever so slightly denser than everything around them. These denser spots pulled nearby matter toward them under gravity. As matter drained away from the lower density regions, those regions got emptier. Over billions of years, this process amplified. The denser spots became filaments, the emptier spots became voids. Think of it like a city forming from farmland. At first, everyone is spread out evenly, then a few towns attract people. Roads connect the towns. Farms between the roads empty out as people move toward opportunity. Scale that process up across 13 billion years and across billions of light years, and you get the cosmic web. The voids are the farms that emptied out, except the scale is almost impossible to hold in your head. A single large void can stretch for hundreds of millions of light years in every direction. The matter that once lived inside drained outward, pulled toward the denser walls and filaments at the edges. Over time, the interior became cleaner, emptier, quieter. But here is the thing about voids that most people don't realize. They are not truly empty. A handful of galaxies survive inside them, isolated from everything, cut off from the gravitational chaos that shapes galaxies in the denser parts of the web. Those lonely survivors are called void galaxies, and they behave differently from every other galaxy we know. More on them soon. For now, what matters is this. The cosmic web explains why voids exist. Gravity drains matter out of low-density regions and piles it into high-density ones. The process is slow, steady, and ongoing. Voids grow over time, they get wider, emptier, and more extreme the longer the universe runs. Which raises a problem. The Boötes void is so extreme that the standard timeline of cosmic history doesn't fully account for it. Gravity alone, working across the age of the universe, should not have been able to carve out something that large and that empty. So either our understanding of gravity is incomplete, or something else is going on. The answer starts to get clearer once you understand what lives at the edge of every void, pulling matter outward like a slow, invisible tide. And that force is stranger than it first appears. 330 million light years. That number gets used, and most people nod and move on. But stop for a second. Really try to feel it. Light is the fastest thing in the universe. It crosses the length of a football field in less time than a single nerve impulse in your brain. It travels from the Earth to the Moon in just over a second. It reaches the Sun in about 8 minutes, and it crosses our entire galaxy, the Milky Way, in 100,000 years. The Boötes void is 330 million light years wide. That means light leaving one side of this void, traveling at full speed without stopping, takes 330 million years to reach the other side. If that journey had started when the first complex animals were just appearing on Earth, the light would still be in transit right now. The Milky Way could fit inside the Boötes void billions of times over. Billions. Every star you've ever seen in the night sky, every planet in our solar system, every galaxy in our local neighborhood, all of it would disappear inside that void and leave almost no trace. Now think about what should be inside it. Standard cosmological models predict that a region of space 330 million light years wide should contain roughly 2,000 galaxies. Each of those galaxies would hold hundreds of billions of stars. The gravitational interactions between them would be constant, complex and rich with activity. There would be collisions, mergers, bursts of star formation, an entire ecosystem of cosmic events happening across that space. The Boötes void contains 60 galaxies, 2,000 expected, 60 found. Scientists have a word for when observations contradict the model this badly. They call it tension, as in the model is being pulled in one direction and the data is pulling in another, and the distance between them is growing. One of the most striking ways to understand the scale of the Boötes void is this. If the Milky Way was sitting at the center of it, astronomers on Earth would have had no idea other galaxies existed until the 1960s. The nearest galaxies would have been so far away, so faint, that even the best telescopes built before the mid-20th century couldn't have spotted them. We would have assumed the Milky Way was the entire universe. That thought is worth holding for a moment. An entire civilization could develop, build science, study the sky for thousands of years, and never know the universe extended beyond their single galaxy. Because the Boötes void is so large, so empty, that the darkness itself hides everything. Scientists still don't know exactly how the void reached this size. The leading idea is that several smaller voids merged over billions of years, combining into one enormous hole, but the math on how fast that could happen under standard gravity is uncomfortable. The universe isn't old enough for gravity to have done this job completely on its own, at least under the rules we currently use. Something either helped, or our rules are missing something. And the 60 galaxies surviving inside the void make the mystery deeper. They form a loose chain through the interior, like survivors clinging to a rope across an ocean of nothing. Their arrangement suggests structure, even in the emptiness. The void has a shape, a skeleton, and figuring out why leads somewhere completely unexpected. Every model has rules. The standard model of cosmology, the one scientists use to describe the entire history and structure of the universe, comes with a foundational assumption baked into its core. It is called the cosmological principle, and it says this: on the largest scales, matter in the universe is spread roughly evenly in all directions. No region is especially full. No region is especially empty. Zoom out far enough, and everything averages out. This isn't a guess. It was tested against decades of observations. The cosmic microwave background, the faint glow left over from the early universe, looks almost perfectly smooth in every direction. The large-scale structure of galaxy surveys matched predictions. The model worked. Then came the Boötes void. A void 330 million light-years wide, with 97% of its expected galaxies missing, is a direct challenge to the cosmological principle. If matter is supposed to be roughly even on large scales, a region this empty shouldn't exist. The deviation is too extreme. The gap between prediction and observation is too wide. Scientists didn't abandon the model immediately. They adjusted, they argued, they looked for explanations that could save the cosmological principle while still accounting for the void. One argument, maybe the survey was too narrow. Maybe Kirshner's team happened to catch an unusual slice of sky and the void looks bigger than it is because of how the data was collected. Later surveys checked. The void is real. The size holds up. Another argument. Maybe voids of this size are rare but possible under standard physics, just at the extreme tail of what the model allows. Some simulations suggest that extremely large voids can form if conditions in the early universe were just right. But those simulations require the void to be a statistical outlier of enormous magnitude, something that should almost never happen in any universe running under standard rules. Almost never is doing a lot of work in that sentence. When physicists calculate the probability of a void the size of the Boötes void forming under standard cosmology, the numbers come out uncomfortable. The void sits so far outside what the model predicts that it forces a choice. Either the cosmological principle needs revision, or some physics we haven't accounted for is shaping the universe at its largest scales. That second option is serious. It means gravity might behave differently across vast distances than it does locally. Or dark matter, the invisible substance scientists believe holds the cosmic web together, might have properties we haven't measured. Or the expansion of the universe itself might not be as uniform as assumed. Every one of those options would rewrite major sections of physics. And here is the part that should sharpen your attention. The Boötes void is not the only void pushing these questions. It was the first, the most obvious, the one that started the alarm. But as telescope technology improved and surveys grew larger, astronomers began to see that the Boötes void was pointing towards something even bigger. The universe wasn't just hiding one enormous hole somewhere out in deep space. Astronomers would eventually discover evidence that our own galaxy, the Milky Way, the one we live in, might be sitting inside a void of its own. A void so large, it makes the Boötes void look like a minor gap. That discovery came in 2013, and it changed everything. For most of human history, we assumed we were in a normal place, not the center of the universe. Scientists gave that idea up centuries ago, but a typical spot. An average location in an average galaxy in an average stretch of the cosmos. The universe is enormous, and we're in one unremarkable corner of it, surrounded by the same kind of stuff that fills everywhere else. In 2013, 3 astronomers at the University of Hawaii started questioning that assumption. Ryan Keenan, Amy Barger, and Lennox Cowie were studying the distribution of galaxies around us, mapping how matter is arranged in our local neighborhood of the universe. They weren't looking for anything extraordinary, they were filling in details on an existing map. What they found was a hole. Their research proposed that the Milky Way sits near the center of a massive, underdense region of space, a void roughly 2 billion light-years across. They named it the KBC void, using the first letters of their last names. Later, it picked up a second name, the local hole. 2 billion light-years. Sit with that for a second. The Boötes void, the one that shocked astronomers in 1981, spans 330 million light-years. The KBC void is roughly 6 times wider. If the Boötes void is a pothole, the KBC void is the Grand Canyon, except the Grand Canyon stretches from one side of the observable universe to a significant fraction of the other. The matter density inside the KBC void runs about 20 to 30% below the cosmic average. That means for every 10 units of matter the universe typically holds in a given region, the space around us holds only 7 or 8. The missing matter drained toward the denser regions at the void's edges, billions of light years away. And here is the part that hits hardest. The Milky Way is sitting near the center of this thing. Earth, the solar system, every human who has ever lived, every telescope ever built and pointed at the sky, all of it is located inside one of the largest underdense regions ever identified in the observable universe. We didn't know. For decades, astronomers mapped the distant universe and built detailed models of cosmic structure, all while sitting inside an enormous hole without realizing it. Every measurement they took, every calculation they ran about the expansion rate of the universe, every survey of nearby galaxies, all of it was done from inside a void that quietly skewed the results. The implications of that are enormous. If the space around us has 30% less matter than average, then the gravitational behavior of our local region is different from the cosmic norm. Light passing through this region travels differently. Galaxies around us move differently. The local universe looks different from the inside of a void than it would from a typical location. Scientists are still working out exactly how much this matters, but one consequence jumped out immediately, and it pointed directly at one of the most heated arguments in modern astronomy. The KBC void might explain why 2 very different measurements of the universe's expansion rate refuse to agree with each other. That disagreement has a name. It has been growing for years, and it suggests that something in our understanding of the universe is fundamentally broken. Step inside the Boötes void for a moment. Imagine floating in space, far from any galaxy, surrounded by darkness in every direction. No nearby stars, no galaxy clusters blazing in the distance. Just the faint cold light of 60 isolated galaxies scattered across 330 million light-years of near-total emptiness. Now look closer at where those 60 galaxies sit. They are not scattered randomly across the void. If they were just leftover matter that gravity hadn't cleared out yet, you'd expect them to be spread across the interior in a loose, irregular pattern. Instead, They form a loose chain, a tube-like arrangement running through the central region of the void, connected by faint threads of gas like a necklace draped across an enormous dark room. Scientists call structures like this filaments. Even inside a void, where matter has been almost entirely cleared out, the remaining galaxies organize themselves along these thin threads of gas, rather than drifting freely. The void has a skeleton. Why does that matter? The arrangement suggests that even in the emptiest regions of the universe, gravity hasn't stopped working. The 60 surviving galaxies are still being pulled along faint lines of slightly denser material, connecting them across the darkness. The void is empty, but it still has structure. That structure tells a story about how the void formed. One hypothesis: the Boötes void started as multiple smaller voids. Each smaller void had its own filament network. As the smaller voids expanded and merged, their internal filaments got pushed together, squeezed into the chain we observe today. The 60 galaxies are the survivors of that merging process, remnants of the filament networks that used to divide separate voids. But this hypothesis runs into a timing problem. For several smaller voids to merge into something the size of the Boötes void, under standard gravity and within the age of the universe, the numbers barely work. Some models suggest it's possible at the extreme edge of what's allowed. Others say the timeline is too tight even under the most generous assumptions. The surviving galaxies carry another secret too. Void galaxies, the ones that exist inside large empty regions, tend to be isolated from the violent gravitational interactions that reshape galaxies in denser parts of the universe. Out in the crowded cosmic web, galaxies collide, merge, and trigger massive bursts of star formation. In a void, none of that happens. A void galaxy grows slowly, quietly, feeding only on the sparse gas available to it, undisturbed by neighbors. Those 60 galaxies inside the Boötes void have been sitting in near total isolation for a very long time. And isolation does strange things to a galaxy. Without collisions, there are no merger-driven starbursts. Without nearby clusters pulling gas away, a void galaxy holds onto its raw material longer. It evolves differently, at its own quiet pace, following a path that most galaxies in the universe never get to take. Scientists want to understand that path, and one galaxy in particular, sitting deep inside another void entirely, has become the focus of that search. It is one of the loneliest objects ever catalogued, and studying it might teach us something fundamental about how galaxies actually form. The voids we see today were not carved out yesterday. They are the result of a process that started less than a second after the Big Bang, in conditions so extreme that the universe barely resembles anything we can picture. To understand why voids exist at all, you have to go back to the very beginning. In the first fraction of a second after the Big Bang, the universe was a single, unimaginably hot and dense point of energy. It expanded at explosive speed. As it expanded, it cooled. And as it cooled, matter began to form, electrons and protons condensing out of the energy like steam turning to water. For roughly the first 380,000 years, the universe was so hot and dense that light couldn't travel freely. Everything was tangled together, a thick fog of matter and radiation. Then the temperature dropped enough for electrons to bond with protons, forming neutral atoms. The fog cleared. Light streamed outward in every direction. That light is still traveling today, and we detect it as the cosmic microwave background, the faint afterglow of the early universe. But here is the piece that matters most for understanding voids. Even in that early fog, the universe was not perfectly smooth. Quantum mechanics, the physics governing things at the smallest possible scales, guarantees tiny random fluctuations in energy density. Some spots were fractionally denser than others, just slightly, by an amount so small it seems impossible that it could matter. Those tiny density differences were the seeds. The fractionally denser spots pulled nearby matter toward them under gravity. Matter drained away from the slightly less dense regions. Over millions of years, then hundreds of millions, then billions, this process amplified. The denser spots attracted more matter, which increased their gravity, which attracted more matter still. The less dense spots got emptier as their matter was pulled away. Think of it like a bathtub of water with slight bumps in the bottom. Water flows toward the low points fill up, the high points dry out. Except in the universe, the low points are what became galaxy clusters and filaments, and the high points are what became voids. The pattern you see in the cosmic web today, those vast threads and walls and emptiness, traces directly back to those microscopic quantum fluctuations in the first moment of the universe's existence. The Boötes void exists because a patch of the early universe happened to be fractionally less dense than everything around it. That tiny head start compounded over 13 billion years into a whole 330 million light years wide. The universe turned a whisper into a shout. And here is where it gets uncomfortable. Standard models of how those fluctuations grew over time predict voids of a certain maximum size. Run the simulations. Let gravity do its work for 13 billion years. The biggest voids the models produce comfortably are around a few 100 million light years across. The Boötes void fits that range barely. But another void, the one surrounding our own galaxy, stretches 2 billion light years across. That is well outside what the standard models produce without serious strain. Something either helped the voids grow faster, or the initial fluctuations were larger than the standard model predicts. Either answer forces physicists to revisit assumptions they've held for decades, and the deeper those physicists dig, the stranger the picture becomes. Most galaxies live crowded lives. The Milky Way has the Andromeda galaxy closing in on it. Both sit inside a group of dozens of galaxies called the local group. Beyond that, the local group is gravitationally bound to larger clusters and superclusters. Every galaxy in our neighborhood is being pulled, pushed, stretched, or compressed by the gravity of its neighbors. Constantly. That gravitational chaos shapes everything. It triggers collisions, it strips gas from one galaxy and feeds it to another, it compresses clouds of gas until they explode into new stars. The violence of a dense cosmic environment is also what drives most of the galaxy growth we observe. Void galaxies live a completely different kind of life. Void galaxies are galaxies located deep inside cosmic voids, far from the filaments and walls where most galaxies cluster. They are rare, they are isolated. And because of that isolation, they evolve in ways that most galaxies never experience. Without nearby neighbors, there are no gravitational encounters to strip away gas. Without collisions, there are no merger-driven bursts of star formation. A void galaxy grows slowly, fed only by the thin streams of gas available in its near-empty surroundings. It holds onto its original material longer. It changes more gradually. It is, in a sense, a galaxy in slow motion. Astrophysicists consider void galaxies to be some of the most valuable objects in the observable universe for understanding how galaxies actually form. In the crowded parts of the cosmic web, galaxy evolution is messy. Collisions add noise, gravitational interactions complicate the picture. A void galaxy strips all of that away. It shows what galaxy formation looks like in its simplest, most undisturbed state. Think of it like trying to understand how a bonfire burns while standing in the middle of a fireworks show. The noise drowns out the details. A void galaxy is the bonfire in an open field, far from everything else, burning clearly. Scientists have found that void galaxies tend to be bluer and more actively forming stars than average despite being isolated. This surprised researchers. Conventional thinking suggested that galaxies cut off from fresh gas inflows would slow down and redden over time, becoming quieter and older looking. Instead, many void galaxies appear relatively young and active, suggesting they have access to intergalactic gas in ways that denser environments don't allow. The sparse gas threads stretching through the interior of a void feed these galaxies slowly but steadily. The connection is faint, the supply is thin, but it keeps the galaxy alive and active in ways scientists are still working to explain. Exactly how void galaxies maintain their star formation rates over billions of years, without the gas-rich mergers that fuel galaxies in denser environments, is one of the open questions in modern galaxy science. The current models don't fully account for it. Every void galaxy found adds a data point to that puzzle, and one of them, Sitting deep inside a void, far from any significant neighbor, has become a centerpiece of that research. It's a galaxy so isolated that astronomers gave it a quiet, unremarkable name in a catalogue of millions. But what it represents is anything but quiet. The story of that galaxy and what it reveals about isolation on cosmic scales connects to something much larger, something that raises a question about our own galaxy's future. Its catalogue name is forgettable. Its situation is extraordinary. The galaxy known as MCG plus 0102015 sits deep inside a cosmic void, surrounded by nothing for extraordinary distances in every direction. The nearest significant galaxy cluster is so far away that the gravitational influence of that cluster is essentially zero. This galaxy has been growing, aging, and forming stars entirely on its own for billions of years. MCG plus 0102015 is considered one of the most isolated galaxies ever catalogued. Astronomers classify it as a void galaxy, meaning it formed and evolved inside a large underdense region rather than along one of the filaments or walls where most galaxies live. Its isolation is so extreme that it provides scientists with something very difficult to find anywhere else in the observable universe. A galaxy that has never been significantly disturbed by its environment. Why does that matter? When astronomers study typical galaxies, they're looking at objects shaped by billions of years of interactions. Mergers, close passes, gas stripping, tidal forces from neighboring clusters. Every galaxy in a dense environment carries the fingerprints of those interactions, and separating them from the galaxy's intrinsic properties is extremely difficult. MCG plus 0102015 has almost none of those fingerprints. Whatever it looks like today reflects its own internal evolution, not the chaos of a crowded neighborhood. It is a control sample, a baseline, the galaxy equivalent of a lab experiment run in total silence. Studies of void galaxies like this one show that they tend to form their stars at a slower, steadier rate than galaxies in denser regions. Without mergers triggering sudden bursts of star formation, the process is gradual. The galaxy uses its available gas carefully, sustaining a lower but more consistent level of activity across longer timescales. This has a strange implication. Galaxies in dense regions tend to burn bright and fast. They collide, they trigger starbursts, they consume their gas quickly, and eventually they quiet down into old red star-poor systems. Void galaxies like MCG plus 0102015 may avoid that fate for much longer. They burn slowly. They stay active. They may still be forming stars long after their cousins in crowded clusters have gone quiet. Whether this extended star-forming life gives void galaxies a fundamentally different evolutionary endpoint is still an open question. Scientists suspect it does, but the timescales involved are longer than human civilization has existed, and the data is still coming in. What MCG plus 0102015 reveals most powerfully is this: location matters enormously in the universe. The same galaxy, placed in a different environment, would look completely different today. The cosmic web is not a passive backdrop. It actively shapes every object inside it. And the void does not just shape galaxies, it shapes measurements. Scientists standing inside a void, using telescopes built inside that void, looking out at a universe filtered through that void, get a distorted picture without realizing it. Every measurement they take is subtly colored by their location, which brings us back to our own situation. The Milky Way is inside the KBC void. Earth is inside the Milky Way. Every observation ever made from this planet, every calculation about the size and age and expansion rate of the universe came from inside an enormous hole in space. And that hole has been quietly bending our measurements for decades. Before you can find a void, you have to be able to measure the universe in 3 dimensions. That sounds obvious, but for most of human history, astronomers could only see where things were on the sky, their position in 2 dimensions, like dots on a photograph. They couldn't tell how far away anything was. Everything from the moon to the most distant galaxy was flattened into the same flat picture above them. The tool that changed everything is called redshift. When a galaxy moves away from us, The light it emits gets stretched. The faster the galaxy moves away, the more the light stretches toward the red end of the spectrum. By measuring exactly how red a galaxy's light is, astronomers can calculate how fast it's moving away from us. And since the universe is expanding at a known rate, that speed translates directly into a distance. This is how Kirshner's team built their map in 1981. They measured the redshift of hundreds of galaxies across a slice of sky, converted those measurements into distances, and plotted every galaxy in three-dimensional space. The result was the first detailed large-scale map of the nearby universe. And that map showed the great nothing. Redshift surveys expanded rapidly after that discovery. Astronomers mapped wider slices of sky, reached greater distances, and built increasingly detailed three-dimensional pictures of the cosmic web. Each survey confirmed the same basic structure: filaments, walls, clusters, and voids. The cosmic web was real. The question shifted from whether voids existed to how large they could get and what rules governed them. Getting an accurate redshift requires collecting enough light from each galaxy to analyze its spectrum. For faint, distant galaxies, that takes significant telescope time. Early surveys were limited in depth and coverage, mapping only the nearby universe in detail. As telescopes improved, surveys pushed further out, revealing larger structures and bigger voids. But here is the complication that most people don't think about. When astronomers measure redshift, they are measuring a combination of two things: the galaxy's motion due to the universe's overall expansion, which is what tells you the distance, and the galaxy's own local motion through space, driven by the gravity of nearby clusters and filaments. Those two signals are mixed together in every measurement. In the crowded parts of the cosmic web, where massive clusters pull galaxies toward them at high speeds, this mixing creates significant errors. The inferred distances can be off by tens of millions of light years in extreme cases. Inside a void, the situation is different. Galaxies in a void have very little local gravitational motion. Their redshift is almost purely the result of the universe's expansion. Ironically, a void is one of the cleanest places in the universe to measure cosmic distances accurately. This is one reason why the KBC void is so scientifically valuable. If we are sitting inside it, then our local measurement of how fast the universe is expanding should be cleaner than average in some respects and noisier in others, depending on how the void's edge affects the light paths we're measuring. Working out exactly which measurements are affected and by how much is one of the central projects of modern observational cosmology. And it connects directly to a problem that has been breaking physicists' sleep for years. Every scientific model needs a foundation. The standard model of cosmology, the one that explains the Big Bang, the cosmic microwave background, the formation of galaxies and stars and everything else, rests on a single core assumption. Remove it, and the entire structure has to be rebuilt from scratch. That assumption is called the cosmological principle. The cosmological principle states that, on the largest scales, the universe looks the same in every direction and from every location. No special spots, no preferred directions. Matter distributed so evenly across cosmic scales that no single region is dramatically fuller or emptier than any other. The universe is, in the language physicists use, homogeneous and isotropic. This principle didn't come from wishful thinking. It came from evidence. The cosmic microwave background, the faint light left over from 380,000 years after the Big Bang, is almost perfectly uniform across the entire sky. Temperature variations exist, but they are tiny, on the order of 1 part in 100,000. That near-perfect uniformity is the strongest direct evidence for the cosmological principle we have. Large-scale galaxy surveys backed it up further. Zoom out far enough, across distances of several billion light years, and the distribution of galaxies looks roughly even in all directions. The cosmic web has structure on smaller scales, but at the largest scales, the clumps and voids average out. Or so it appeared. The cosmological principle is foundational because almost every calculation in modern cosmology depends on it. The equations used to describe the universe's expansion, the predictions for how much dark matter exists, the timeline of galaxy formation, All of it assumes the principle holds. If it breaks down, even partially, at certain scales, those calculations produce wrong answers. The Boötes void was the first serious challenge, a 330 million light-year hole with 97% of its expected galaxies missing, pushed the edges of what the standard model allows, but didn't decisively break the cosmological principle. Scientists argued it was a rare outlier, not proof of a deeper problem. Then came structures that made the Boötes void look small. Beyond the KBC void, astronomers have identified a structure called the Hercules Corona Borealis Great Wall, a vast concentration of galaxy clusters spanning roughly 10 billion light-years. If confirmed at that scale, it would be far too large to be consistent with the cosmological principle. The universe shouldn't be able to maintain structure on that scale and still be homogeneous at larger ones. The accumulation of these structures has forced a quiet but serious debate inside cosmology. Some researchers argue the cosmological principle needs revision. Others say it holds, but the standard model needs new ingredients. A smaller group argues the principle might be wrong entirely. Nobody has definitive proof yet either way, but the structures keep showing up. Each new survey reveals something that strains the model a little further. And the KBC void sits at the center of that debate, literally and figuratively. Because we are inside it, everything we measure about the universe passes through it. Our data is filtered by our location in ways that are difficult to fully untangle, which means the cosmological principle might be right, but our view of the universe might still be skewed in ways we haven't fully corrected for. And if that's true, our most reliable measurement of the universe's expansion rate might be wrong. In 2013, 3 astronomers published a paper that quietly shifted the ground under modern cosmology. Ryan Keenan, Amy Barger, and Lennox Cowie weren't making a dramatic announcement. They were presenting data from a survey of galaxy counts across different distances from Earth. The data showed something subtle at first. There were fewer galaxies nearby than the standard model predicted. The deficit wasn't enormous, but it was consistent across multiple survey directions. Their conclusion was careful and specific. We appear to live inside a large, underdense region of space, a void extending roughly 2 billion light-years in every direction, with the Milky Way sitting near its center. They named it the KBC void. 2 billion light-years is a number that deserves to be unpacked. The observable universe, the sphere of space we can actually see from Earth, spans about 93 billion light-years in diameter. The KBC void spans 2 billion light-years across. Laid end-to-end, the void would stretch across roughly 2% of the observable universe's full diameter. That is an extraordinary fraction for a single structure. Put it in physical terms, if you shrank the observable universe down to the size of the continental United States, the KBC void would be a region roughly the size of Texas. The matter density inside the KBC void is estimated at roughly 20 to 30% below the cosmic average. This might sound modest, but in cosmological terms, a 30% deficit across a 2 billion light-year region is massive. The amount of missing matter, the galaxies and gas and dark matter that should be there but aren't, represents an enormous underdensity in the fabric of the universe. That missing matter didn't vanish, it drained. Over billions of years as the universe expanded, the slightly denser regions at the void's edges exerted stronger gravitational pull than the interior. Matter migrated outward, toward those denser walls, leaving behind a progressively emptier core. The KBC void is the result of that long, slow drainage, and the Milky Way stayed behind near the center of the drain. The local group, the collection of dozens of galaxies that includes the Milky Way, the Andromeda Galaxy, and their smaller satellites, sits within a few 100 million light-years of the KBC void's estimated center. We are deep inside the emptiness, not at its edge. This has an immediate and significant consequence. From inside a void, the universe looks different than it does from a typical location. The denser walls at the void's edges appear to be receding from us, pulled outward by the void's emptiness. Galaxies at the void's edges seem to be moving away faster than they should be, because the void's low density is effectively pushing them toward the higher density regions beyond. From our vantage point inside the void, that movement looks like extra expansion. The universe appears to be stretching faster locally than the global average would predict. This distortion in apparent expansion rate could be a major piece of one of the biggest unsolved problems in modern physics. Scientists call it the Hubble tension, and understanding it starts with understanding why two completely different methods of measuring the universe's expansion rate give two completely different answers, even though both methods have been checked and rechecked and confirmed dozens of times. Imagine you're underwater. You're not near the surface. You're not near the floor. You're somewhere in the middle of an enormous, quiet body of water with no landmarks in any direction. Looking outward, everything you see is filtered through the water around you. Light bends slightly, colors shift, objects look different than they would from the air. Now imagine you don't know you're underwater. That is roughly the situation astronomers realized we might be in. The Milky Way appears to sit near the center of the KBC void, a region of space with roughly 30% less matter than the cosmic average. Every observation made from Earth passes through that underdense region. Every calculation built from those observations carries the subtle fingerprints of our location. The consequences show up in the data in specific ways. Matter in the universe doesn't just sit still. It flows. Regions of higher density pull matter toward them. Regions of lower density push matter away. Inside the KBC void, the denser walls surrounding the void are pulling galaxies at the void's edges outward, away from the center where we sit. Those galaxies appear to be moving away from us faster than the universe's average expansion rate would predict. From inside the void, looking outward at those edge galaxies, we measure a higher expansion rate than an observer sitting in a typical region of the universe would measure. This is directly relevant to the Hubble tension. Our local measurements of the expansion rate are done by studying nearby galaxies and objects, things within a few 100 million light years. All of those measurements are made from inside the KBC void. If the void is real, and the matter deficit is as large as the 2013 paper claimed, then our local expansion rate measurement is systematically biased upward. The universe isn't expanding as fast as we think locally. We just happen to be sitting in a spot where the local dynamics make it look that way. However, the exact size and depth of the KBC void is still debated. Some independent surveys have measured the galaxy deficit out to certain distances and confirmed a real underdensity. Others have found that the deficit weakens or disappears at larger distances, suggesting the void might be smaller than originally claimed. The debate is active and unresolved. This uncertainty matters enormously. If the void is large enough and deep enough, it could account for most of the Hubble tension on its own. If it turns out to be smaller or shallower than the 2013 estimate, it explains only part of the discrepancy. What is confirmed is that we live in a region of below average matter density. The galaxy count data backs this up across multiple independent surveys, even if the exact boundaries are disputed. We are in a hole. The argument is about how big the hole is. And the implications go beyond just the Hubble tension. If the space around us is significantly underdense, then every cosmological measurement we've made from this location carries a systematic error tied to that underdensity. The age of the universe, the rate of structure formation, the properties of dark energy, all of these involve measurements filtered through our local environment. Getting those measurements right requires correcting for the void, and correcting for the void requires knowing its exact size and shape, which is precisely what astronomers are still arguing about. The universe is moving. Every galaxy, every cluster, every thread of the cosmic web is in motion. Some of that motion comes from the overall expansion of the universe, space itself stretching in every direction. But on top of that expansion, galaxies have their own local velocities, driven by the gravity of nearby structures pulling them this way and that. Inside a void, that local motion takes on a very specific pattern. A cosmic void is a region of below average matter density. The edges of the void, the walls and filaments surrounding it, have above average density. That density difference creates a gravitational gradient, a slow but steady pull directed outward from the void's center toward its denser edges. Matter inside the void migrates outward over time. Galaxies near the void's edge get drawn toward the denser regions beyond it. The void gradually empties further as its interior loses material to its surroundings. From the inside, looking outward, this creates a specific effect on what we observe. Galaxies at the KBC void's edge are being pulled outward, away from us, toward the denser walls surrounding the void. That outward pull adds to their apparent recession velocity, the speed at which they seem to be moving away from us. When astronomers measure how fast those edge galaxies are receding, they get a number that includes both the universe's overall expansion and this extra outward push from the void. The result is a local expansion rate that appears higher than the true cosmic average. Think of it like being at the drain of a bathtub. Water near you is moving toward the drain faster than water on the far side of the tub. If you're measuring how fast water is flowing, your local measurement will be higher than the average flow rate across the entire tub. You're in the spot where the flow is concentrated. Astronomers call this type of outward flow a bulk flow, large-scale motions of galaxies across millions of light years driven by the gravitational pull of surrounding structures. Measurements of the bulk flow around our local region of the universe have confirmed that the galaxies in our neighborhood are moving outward in patterns consistent with a large surrounding underdensity. This is observational evidence that we are indeed inside a void, being pulled toward its edges from our position near the center. If the KBC void is as large as the 2013 survey estimated, 2 billion light years across, with a matter deficit of 20 to 30%, then the extra recession velocity it adds to nearby galaxy measurements could be large enough to explain a significant fraction of the Hubble tension. Researchers like Dr. Indranil Banik have argued that the void, combined with modified theories of gravity, could explain the full discrepancy without requiring any additional unknown physics. The problem is that this solution requires the void to be extremely large and extremely deep, larger and deeper than some independent surveys have found. If later measurements confirm a smaller or shallower void, the explanation weakens. The void's pull is real. The debate is over how strong it is and whether it's strong enough to solve one of modern astronomy's most stubborn problems. That problem has been building for years. 2 measurements, 2 answers, a gap between them that physicists cannot close no matter how carefully they check their work. Every physicist who works on cosmology knows about this problem. 2 different teams, using 2 completely different methods, measured how fast the universe is expanding. Both teams used verified, well-tested techniques. Both were careful. Both double-checked their work. And they got 2 different answers. The gap between those answers is called the Hubble tension, named after Edwin Hubble, the astronomer who first measured cosmic expansion in the 1920s. The expansion rate of the universe is measured in a unit called kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light years. The expansion rate tells you how fast 2 points in the universe are moving apart as space itself stretches between them. Method 1. Measure the expansion directly from nearby objects. Use standard candles, objects whose true brightness is known, to determine precise distances. Then measure how fast those objects are moving away. Astronomers have used pulsating stars called Cepheid variables and exploding stars called Type Ia supernovae for this. The result, roughly 73 kilometers per second per megaparsec. Method 2. Measure the early universe using the cosmic microwave background. Map the precise temperature variations in that ancient light, run the calculations forward using standard physics, and predict what the expansion rate should be today. The result, roughly 67 kilometers per second per megaparsec. That gap of roughly 6 units might sound small, but in the language of physics, the 2 measurements are statistically inconsistent at a level called 5.3 sigma. Sigma is the unit physicists use to measure how far a result sits from what the model predicts. 3 sigma is considered interesting. 5 sigma is the threshold for a genuine discovery. 5.3 sigma means the gap is so large that it almost certainly cannot be explained by random measurement error alone. Something is wrong. Either one or both measurement methods have an unidentified systematic error, or the standard model of cosmology is missing something real. Many explanations have been proposed. Maybe dark energy, the mysterious force driving the universe's acceleration, behaves differently at different times than the standard model assumes. Maybe there's an unknown form of energy in the early universe, called early dark energy, that changed how fast it expanded shortly after the Big Bang. Maybe the standard model's treatment of gravity needs modification at cosmological scales. Every proposed solution has problems. Every patch introduces new tensions somewhere else in the model. The Hubble tension has persisted and grown stronger as measurement precision has improved. A decade ago, some physicists hoped it would shrink as errors were refined. Instead, it remained stubbornly large. The most recent measurements have confirmed both values with increasing precision, and the gap between them hasn't closed. This is one of the most serious open problems in physics, and the KBC void sits directly in the middle of potential explanations. Because if our local measurements are inflated by the outward flow of galaxies inside the void, then the true local expansion rate might be lower than 73. It might be closer to the cosmic microwave background value of 67. The void could be bending our local ruler. How much it bends, it depends entirely on how big and deep the void actually is. Numbers in physics don't lie, but they can mislead. A thermometer left in the sun gives a real temperature. The reading is accurate, but it's measuring the conditions at one spot, under direct sunlight, and calling it the temperature of the air. If you use that number to predict the temperature elsewhere, you get a wrong answer. The instrument is fine. The location is the problem. This is the core argument around the KBC void and the Hubble tension. Our local measurements of the universe's expansion rate are accurate, the instruments work, the methods are sound, but they're being taken from inside an enormous underdense region of space, and that location adds a systematic bias to the results. Here's the chain of logic. The KBC void has roughly 30% less matter than the cosmic average. That deficit creates a gravitational gradient. The denser walls surrounding the void pull matter outward. Galaxies near the void's edge are being accelerated away from us. When astronomers measure those galaxies' recession velocities to calculate the local expansion rate, they're measuring a velocity that includes both the universe's expansion and an extra push from the void. If you strip out the void's contribution, the local expansion rate would drop. How much it drops depends on the void's size and depth. Researchers who model this effect find that a void the size of the KBC void could inflate the measured local expansion rate by enough to explain most of the 5.3 sigma gap between the two. Hubble measurements. If this is right, the Hubble tension is at least partly a measurement artifact. We're not measuring the universe wrong. We're measuring our void correctly and then applying that measurement to the universe as a whole, which is wrong. Dr. Indranil Banek and colleagues have published work arguing that the KBC void, combined with a modified theory of gravity called Milgromian dynamics, can explain the Hubble tension in full. Their model predicts a local expansion rate consistent with the distance ladder measurements, while also being consistent with the cosmic microwave background at large scales. The challenge is that this solution requires the KBC void to be real, large, and deep. And some independent surveys cast doubt on those properties. Several teams have measured galaxy distributions at the distances where the void should be most prominent, and found a smaller or weaker underdensity than the 2013 paper claimed. The debate is genuine. Scientists on both sides have data. The resolution will require larger, more detailed surveys covering the full 2 billion light-year extent of the proposed void. What is not in doubt is that our position in the universe matters for measurement. The cosmic web is not a neutral backdrop. Our location inside or outside a void, near or far from a massive cluster, on the edge of a filament or inside one, affects every cosmological measurement we take. Correcting for location is a real and necessary part of getting the numbers right, and the stakes go beyond just one constant in one equation. If the void is real and large, it means the universe is more structured on enormous scales than the standard model predicted. That implies the cosmological principle, the assumption that matter is evenly spread on large scales, breaks down at smaller scales than previously thought, which breaks more than just the Hubble constant. It breaks the foundation the entire model sits on. The simulations saw this coming, and the numbers they produced were so extreme that physicists checked them 3 times before accepting what they showed. Science builds models to test ideas. You can't run a real experiment on the universe. You can't move galaxies around or change the rules of gravity and see what happens. So physicists build simulations, mathematical models of the universe running on supercomputers, designed to test whether the physics we understand produces the structures we observe. If the simulation matches reality, the model is probably right. If it doesn't, something is missing. In the case of the KBC void, the simulation gave an answer that made physicists stop and stare. The simulation used to test the KBC void is called the Millennium XXL simulation, one of the largest and most detailed computational models of cosmic structure ever built. It models a volume of space large enough to contain millions of galaxy clusters, running the standard rules of physics forward from the Big Bang to the present day. Researchers use this simulation to answer one question. Under standard cosmology, how often would a void the size and depth of the KBC void appear? The answer, published in a peer-reviewed paper, was expressed as a sigma value. The KBC void's existence in the standard model showed a tension of 6.04 sigma. That number means the probability of such a void forming under standard physics is so small that it is effectively zero. In the entire simulated volume, which was enormous, a void matching the KBC void's properties essentially never appeared. 6 sigma is not just unusual. In particle physics, 5 sigma is the threshold for claiming a new discovery. The KBC void sits above that threshold in the wrong direction, meaning the standard model actively predicts it should not exist. This is where the result becomes genuinely unsettling. A 6 sigma tension is strong enough that in any other field of physics, it would force an immediate revision of the underlying model. If a prediction of the standard model of particle physics were off by 6 sigma, physicists would already be rewriting the textbook. In cosmology, the debate is more complex, partly because the measurements are harder and the uncertainties are larger, but the tension is real and serious. One response from cosmologists is to argue that the simulations are not perfect. They depend on assumptions about how dark matter behaves, how dark energy evolves, how baryonic matter, the ordinary stuff made of protons and neutrons, interacts with everything else. Small errors in those assumptions could compound over billions of years and produce a simulation that doesn't perfectly reflect the real universe. That's a fair point, but the magnitude of the discrepancy is large enough that fixing it through minor simulation tweaks is extremely difficult. The more serious response is to consider that the standard model, specifically its treatment of gravity on large scales, is genuinely incomplete. Milgromian dynamics, the modified gravity theory mentioned in the Hubble tension context, predicts that gravity behaves differently on large scales than standard physics assumes. Under Milgromian dynamics, voids can grow faster, reaching larger sizes in the same amount of time. The KBC void's existence becomes more plausible. Whether Milgromian dynamics is the right modification or whether some other extension of physics is needed is unknown. No single alternative theory has yet explained all the observations simultaneously. What the simulation revealed is that the universe we live in looks different from the universe the standard model predicts. The gap between them is measurable, consistent, and statistically very hard to dismiss. The KBC void is where that gap is most visible. And the deeper scientists look into it, the more they find that the standard model's foundations may be under stress in ways nobody fully anticipated. The simulation said impossible, the universe said otherwise, and that disagreement is still waiting for an answer. Numbers tell stories, but only if you know how to read them. When scientists report a result, they attach a confidence level to it. That confidence level tells you how unlikely it is that the result happened by random chance. The unit they use is called sigma. 1 sigma means the result is mildly unusual. 2 sigma means it's starting to get interesting. 3 sigma means something real might be going on. 5 sigma is the threshold for a confirmed discovery in physics. The 5 sigma standard exists because physics demands certainty before rewriting textbooks. When scientists at CERN announced the discovery of the Higgs boson in 2012, the result had cleared 5 sigma. When gravitational waves were detected for the first time in 2015, the signal cleared 5 sigma. 5 sigma means the probability that the result is a statistical accident is less than 1 in 3.5 million. That is the bar, and it is high on purpose. Now consider what 6.04 sigma means for the KBC void. The Millennium XZS simulation, running the standard rules of cosmology forward from the Big Bang, produced a 6 sigma tension when it tried to account for a void the size and depth of the KBC void. 6 sigma means the probability of that void existing under standard physics is less than 1 in 500 million. To put that in terms a person can feel, if you ran the universe over and over again, each time starting from the same initial conditions and letting it evolve under the same standard physics, you would have to run it roughly 500 million times before you'd expect to see a void like the KBC void appear even once. We appear to live in one. Here is where it gets philosophically uncomfortable. Scientists sometimes argue that improbable things happen. The universe is vast. Rare events occur somewhere simply because the universe is large enough to contain them. A 6 sigma event is rare, but the observable universe contains an enormous number of possible locations where extreme structures could form. This argument has limits though. The KBC void is centered on our location. We are near its center. The probability calculation already accounts for the size of the observable universe. The tension is not merely that such a void exists somewhere, it's that we happen to be inside it, and that our location inside it is what caused us to notice the Hubble tension in the first place. If the standard model is correct and the void is real, then we occupy one of the most statistically improbable addresses in the observable universe. An address so unlikely that many physicists consider this a signal that the standard model is missing something fundamental, rather than evidence that we simply got cosmically unlucky. The alternative is that the void is not as large or deep as the 2013 measurements suggested, and the true sigma tension is lower. This would make our situation less improbable, but would also reduce the void's ability to explain the Hubble tension. The sigma number is not just a measure of strangeness, it is a diagnostic tool. It tells scientists how hard their model is straining to accommodate an observation. 6 sigma is the model screaming, and the standard model has been screaming about the KBC void for years. The question physicists are now forced to ask is whether the model needs a patch, or whether it needs to be rebuilt from a new foundation. That question leads directly to one of the oldest debates in physics. How does gravity actually work at the largest scales? Gravity is the force that built everything. It pulled hydrogen atoms together into stars. It held stars together into galaxies. It threaded galaxies into the cosmic web. Every structure in the observable universe exists because gravity kept pulling matter toward matter across billions of years. So when scientists say gravity might not be enough to explain what we observe, that is a serious claim. Standard gravity, described by Einstein's general theory of relativity, works extraordinarily well at most scales. It predicts the motion of planets, the bending of light around massive objects, the existence of gravitational waves, and the overall expansion of the universe. Every precision test of general relativity has confirmed it to high accuracy. The problem shows up at the largest scales, where the structures being explained, galaxy rotation curves, the behavior of galaxy clusters, and now the size of cosmic voids, don't match what standard gravity predicts without adding invisible ingredients. Dark matter was introduced partly to solve one of those mismatches. Galaxies spin faster at their edges than the visible matter inside them can account for. Add a halo of invisible, gravitationally active dark matter around each galaxy, and the rotation curves fit. Dark matter became a cornerstone of the standard model of cosmology. But dark matter, as currently modeled, still struggles to explain how the KBC void got so large so fast. An alternative framework called Milgromian dynamics developed by physicist Mordechai Milgrom in the early 1980s, proposes that gravity behaves differently at very low accelerations. Below a certain threshold of gravitational acceleration, one that is extremely small by everyday standards, gravity becomes stronger than Einstein's equations predict. This modification was originally proposed to explain galaxy rotation curves without dark matter. The interesting result is that Milgromian dynamics also changes how cosmic voids grow. Under standard gravity, voids expand at a certain rate controlled by the balance between the universe's expansion and the gravitational pull of surrounding matter. Under Milgromian dynamics, gravity at the low-density edges of voids behaves differently, and voids can grow larger and faster. A void the size of the KBC void becomes more plausible within the age of the universe, under this framework. Whether Milgromian dynamics is the correct description of gravity at large scales is deeply contested. It explains some observations well and struggles with others, particularly the behavior of galaxy clusters, which dark matter handles more naturally. No single modified gravity theory has yet explained all cosmological observations simultaneously. But the fact that standard gravity, even with dark matter, struggles to produce the KBC void in the time available is significant. It means the void is not just a measurement puzzle, it's a gravity puzzle. The universe built a structure that our best theory of how things fall toward each other can't easily account for. Either the void is smaller than measured, and the problem shrinks, or the void is real, and something about gravity on the largest scales is different from what the equations say. Both possibilities are uncomfortable. One means our measurements are wrong, the other means our physics is incomplete. And the deeper astronomers look into the void's interior, the more they find that emptiness itself behaves in ways the standard picture doesn't fully predict. The cosmological principle says the universe has an average zoom out far enough. It says, and matter smooths out. No region is dramatically fuller or emptier than any other. The universe has a baseline density, and everything averages toward it on the largest scales. That assumption is load-bearing. It holds up the entire mathematical structure of modern cosmology. If the cosmological principle is correct, then the equations describing the universe's expansion, the predictions for how structure forms over time, and the calculations connecting early universe observations to present-day measurements all work as intended. The standard model depends on the universe having a true average density that regions converge toward at large enough scales. The KBC void challenges that assumption directly. A void 2 billion light-years across, with matter density 30% below average, sitting near the center of our observable region, is hard to reconcile with a universe that averages out at large scales. If such a dramatic underdensity exists, and if similar large-scale structures exist elsewhere, the universe may not converge to a smooth average at any scale we can observe. This is what some cosmologists call a fractal universe hypothesis. The idea is that the cosmic web structure, with its clumps and voids and filaments, repeats at larger and larger scales without ever smoothing out. There is no scale at which you zoom out and see a truly uniform distribution. If the universe is fractal in this sense, the cosmological principle is wrong. Every measurement that depends on it, including the Hubble constant, the age of the universe, the properties of dark energy, would need to be recalculated without that assumption. The equations would need to be rebuilt. Most cosmologists do not accept the fractal hypothesis. Observations at the very largest scales, particularly the cosmic microwave background, and surveys extending beyond 10 billion light-years, appear consistent with the cosmological principle at those extremes. The universe does seem to smooth out eventually. The debate is about where the smoothing starts, and whether the KBC void sits within the range where the principle should already hold. The honest answer is that current surveys don't reach far enough with enough detail to definitively answer whether the cosmological principle holds at the scale of the KBC void. The void is enormous. Mapping its full extent requires observations at distances where galaxy surveys are still relatively thin. But the question itself is significant. For most of cosmology's history, the cosmological principle was treated as nearly axiomatic, a starting assumption so well supported that questioning it felt unnecessary. The accumulation of large-scale anomalies, the Boötis void, the KBC void, and other oversized structures has turned it into an active research question. Some researchers now argue the standard model needs a new ingredient, a mechanism that allows structure to form faster and on larger scales than current physics predicts, without breaking the early universe observations that the model fits well. Finding that ingredient, if it exists, would reshape how we understand the universe's entire history, and the search for it runs through some of the most exotic physics in modern science. 13 billion years ago, the universe was screaming. Sound waves, enormous pressure waves moving through the hot plasma of the early universe, rippled outward from every dense region in every direction. The entire young cosmos was vibrating. For 380,000 years, those waves bounced and rolled through the thick, hot fog of matter and radiation. Then the universe cooled enough for atoms to form. The fog cleared. The pressure waves froze in place, like a sound stopped mid-note, preserved in stone. Those frozen wave patterns are called baryon acoustic oscillations. Baryon acoustic oscillations left a specific imprint on the distribution of matter in the universe. Galaxies today are slightly more likely to be found at a specific distance from each other, roughly 500 million light years, the distance those pressure waves had traveled before they froze. This preferred distance shows up as a subtle statistical bump in galaxy surveys, a faint ring of enhanced galaxy density around every point in the universe. Astronomers use this ring as a cosmic ruler. Because its physical size is known from early universe physics, measuring how large it appears on the sky at different distances gives a precise measurement of the universe's expansion history. Voids distort this ruler. When light or structure passes through a cosmic void, the underdense region affects how baryon acoustic oscillations appear. The void changes the apparent size of the oscillation ring in its vicinity, introducing a subtle shift in the measurement. For small voids, the effect is minor. For a void the size of the KBC void, the distortion is potentially significant. If our local baryon acoustic oscillation measurements are taken from inside the KBC void, the ruler we're using has been quietly bent by the void's underdensity. The distances we infer from those measurements carry a systematic offset. Correcting for the void's distortion would shift our calculated expansion rate, potentially bringing it closer to the cosmic microwave background value and easing the Hubble tension. This is a subtle but powerful point. Scientists use baryon acoustic oscillations as a supposedly clean, standard measurement, one of the most reliable tools in cosmology. But if those measurements are being taken from inside a large void, the tool is compromised in a specific, correctable way. Quantifying exactly how much the KBC void distorts local baryon acoustic oscillation measurements requires knowing the void's precise size and density profile, which is still debated. The distortion could be large enough to matter significantly, or it could be too small to explain much of the Hubble tension on its own. What this reveals is that the universe is never a neutral laboratory. Every measurement is filtered through the environment of the observer. The frozen sound waves from the Big Bang reach us after traveling through billions of years of cosmic structure, including our own local void. We are not measuring the universe from outside it. We are measuring it from inside, from one very specific, very unusual spot. And the unusual nature of that spot extends in all directions, in ways scientists are still mapping. Here is a fact that doesn't get enough attention. The universe is mostly empty. Cosmic voids make up roughly 80% of the observable universe's total volume. The filaments, walls, and clusters that hold nearly all the matter, all the stars, all the galaxies, all the gas and dust and dark matter that make up everything visible, occupy the remaining 20%. The cosmos is, by volume, overwhelmingly made of almost nothing. Think about what that means for a moment. If you picked a random point in the observable universe and teleported there, there's an 80% chance you'd appear inside a void. You'd be surrounded by darkness. No nearby galaxies, no stars visible to the naked eye except for faint smudges at enormous distances. Just the cold, quiet expanse of a region that gravity has spent billions of years emptying out. The universe we see in photographs, crowded with galaxies and glowing with starlight, is the exception. The rule is emptiness. This dominance of voids by volume has real physical consequences. Voids are not passive background features of the cosmic web. They actively push matter outward. As a void expands over time, the slight underpressure at its center drives matter toward its edges, feeding the filaments and walls that surround it. Voids are engines of structure formation, slowly clearing their interiors and piling matter into the cosmic web's skeleton. Some cosmologists argue that voids are actually more important to the evolution of the universe's large-scale structure than the dense regions. The filaments and clusters get most of the attention because they're bright and easy to observe. But the voids drive the dynamics. They push matter around. They shape how clusters grow. The universe's structure is carved by emptiness as much as it is built by density. Voids also expand over time. As the universe grows, voids grow with it, and dark energy, the mysterious force accelerating cosmic expansion, amplifies this growth. In a universe dominated by dark energy, voids eventually win. Over long enough timescales, dark energy accelerates the expansion so much that matter becomes increasingly isolated. The voids grow larger, the filaments thin out, the clusters that remain become islands in an ever-emptying sea. The universe is headed toward more emptiness, not less. Exactly how this long-term evolution plays out depends on the true nature of dark energy, which remains one of physics's deepest mysteries. If dark energy is constant, voids grow at a predictable rate. If it changes over time, the future looks different. But the trajectory is clear. The universe started dense and hot. It expanded and cooled. Structure formed from tiny fluctuations. Matter clumped into filaments and clusters, and the spaces between them, the voids, grew and grew until they swallowed 80% of all available space. We live in the universe's minority, the bright, crowded 20%, or rather, we almost do. The KBC void places us near the border, in a spot that is less crowded than average but still connected to the broader cosmic web. Sitting in that position, between the void's center and its edge, means the universe looks different to us than it does from a truly typical location. And the more scientists study how different it looks, the more they find structures they hadn't anticipated. The Boötes void did not arrive fully formed. Nothing in the universe does. Every structure, every galaxy, every cluster, every void is the result of a long process of growth, merger, and transformation stretching across billions of years. The Boötes void, 330 million light-years wide and nearly empty, has a history, and that history is more complicated than it first appears. The leading hypothesis among cosmologists is that the Boötes void formed through the merger of several smaller voids over an extended period. Early in the universe's history, smaller, underdense regions existed across the volume now occupied by the void. As the universe expanded, those smaller voids grew. Their edges, where their surrounding walls and filaments were, eventually ran into each other. The walls between them thinned and broke. The voids merged into a single, larger void. Think of soap bubbles. When two bubbles touch, the wall between them doesn't stay. It collapses, and the two bubbles merge into one larger sphere. Cosmic voids work similarly, except the process takes billions of years and spans hundreds of millions of light years. The chain of 60 galaxies running through the Boötes void center is consistent with this merger history. Those galaxies likely lived along the internal filaments of the smaller voids before they merged. When the voids combined, those filaments were compressed and pushed toward the center, leaving the galaxy chain we observe today as a fossil record of the void's earlier, more divided structure. The timing problem, however, remains. For several smaller voids to have merged into something the size of the Boötes void within the age of the universe, the individual voids would have had to grow very quickly after the Big Bang. Standard gravity, even with dark matter, produces void growth rates that make this timeline tight. The math works at the very edge of what's allowed, and only under assumptions that some researchers consider generous. Under Milgromian dynamics, void growth rates are faster, and the merger timeline becomes more comfortable. This is one of the observations that modified gravity advocates point to as evidence that standard physics is missing something at large scales. But here is where the story widens in an unexpected direction. If the Boötis void grew by merging smaller voids, the KBC void may have grown the same way. 2 billion light years is too large for a single underdense seed to have grown on its own from the Big Bang to now under any standard model. The KBC void almost certainly absorbed many smaller voids during its growth, incorporating their contents and swallowing their internal filaments. The internal structure of the KBC void is not yet well mapped. Scientists know the void exists from galaxy count data, but they don't yet have a detailed picture of what smaller structures survive inside it, how matter is arranged within its boundaries, or what fossils of previous merger events might be visible in its interior. Future surveys may reveal a more complex internal landscape than currently imagined. A void within a void. Filament fragments from earlier, smaller structures, a record of billions of years of merging written in the arrangement of matter across 2 billion light years. The Boötis void showed us that emptiness has a history. The KBC void suggests that history goes far deeper than anyone expected. Science is not a single voice. For every paper arguing that the KBC void is real, large, and cosmologically significant, there is another paper pushing back. Some researchers accept the void's existence but dispute its size. Others argue the underdensity is real, but shallower than claimed. A smaller group questions whether a coherent void of that scale exists at all. This disagreement is healthy. It is how science works, and in this case, the stakes are high enough that the disagreement is fierce. The original 2013 paper by Keenan Barger and Cowie estimated the void at roughly 2 billion light-years across, based on galaxy counts showing a deficit of roughly 20 to 30% below average. That paper triggered a wave of follow-up studies. Some of those studies confirmed a real underdensity in the local universe. They found fewer galaxies than expected within certain distances in every direction, consistent with living inside a large void. The deficit was real. The void was real. But the size became the argument. Several independent surveys, using different galaxy samples and different methods, found that the underdensity appeared to weaken or disappear at distances beyond about 1 billion light years. If the void's edges are closer than the original estimate, it is roughly half the size claimed. A 1 billion light year void is unusual. A 2 billion light year void borders on cosmologically forbidden under standard physics. The difference matters enormously for the Hubble tension explanation. A smaller, shallower void produces less distortion in local expansion measurements. It explains less of the gap between the two Hubble values. If the void is only half as large as claimed, it cannot account for the full tension on its own, and physicists have to look elsewhere for the rest of the explanation. Defenders of the larger estimate argue that the surveys finding a weaker signal are incomplete. At distances beyond 1 billion light-years, galaxy surveys become sparser and less reliable. The signal from the void's edge might be real, but too faint for current surveys to detect with confidence. Larger, more complete surveys would recover the full extent. Both sides agree that the current data is insufficient to definitively resolve the debate. The surveys that exist are either too shallow, too narrow, or too sparsely sampled at the critical distances to settle the question of the void's true size. This is a genuine scientific standoff. The void's reality is accepted. Its dimensions are contested, and the outcome of that contest has direct implications for whether the Hubble tension is solved, whether the standard model needs revision, and whether the cosmological principle holds at these scales. Resolving the debate will require next-generation survey telescopes capable of mapping galaxy distributions across billions of light-years with much greater density and precision than current instruments. Those telescopes are being built, the data is coming, but until it arrives, the scientific community is working with incomplete maps of the most important void in the observable universe. And in that gap between the data we have and the data we need, the arguments continue. The void is empty, but it is not featureless. stretched across the interior of every large cosmic void, including the Boötes void and possibly the KBC void, are thin filaments of gas. These are not the massive, bright filaments of the cosmic web's main structure. They are faint, tenuous threads, barely detectable with current instruments, connecting the sparse galaxies that survive inside the emptiness. Void galaxies, the rare isolated systems that live inside underdense regions, tend to arrange themselves along these faint threads, rather than drifting freely through the void's interior. The gravitational pull of the thread, weak as it is enough to keep the galaxy tethered. The galaxy feeds from the thread, drawing in gas slowly over billions of years. And these threads have a distinctive property. In the densely packed regions of the cosmic web, filaments are curved, tangled, and complex. The gravitational pull from nearby massive clusters bends them, twists them, redirects their paths. The result is a chaotic tangle of threads, connecting a chaotic tangle of galaxy groups. Inside a void, the situation is different. There are no massive nearby clusters to bend the filaments. The gravitational environment is quiet and simple. The threads running through the void interior are nearly straight. They stretch across hundreds of millions of light years in nearly perfect lines because nothing is strong enough to curve them. This near-perfect straightness is itself a scientific tool. By measuring how straight the filaments inside a void are, researchers can infer the strength and direction of the gravitational forces acting on them. A straighter filament means weaker external gravitational forces. The interior of a void, precisely because it is so empty, provides one of the cleanest measures of gravity's behavior on large scales available anywhere in the observable universe. If gravity behaves differently at low densities than standard equations predict, the filaments inside voids would show subtle deviations from what those equations expect. Their angles, their lengths, their thickness would all encode information about gravitational physics in the low acceleration regime where standard and modified gravity theories diverge most strongly. Detailed mapping of void filaments at sufficient resolution to test these predictions has not yet been done. Current surveys can detect the presence of filaments and their rough orientations, but not the fine-grained properties needed to discriminate between competing gravity theories. This is one of the most compelling scientific arguments for mapping void interiors more precisely. The void's emptiness is not a problem for science. It is an opportunity. The absence of complicating gravitational noise makes the interior of a large void one of the best natural laboratories in the universe for testing fundamental physics. The galaxies strung along those straight, quiet filaments have been evolving in near-total isolation for billions of years. They are slow, steady, and undisturbed. And because of that, they carry information about galaxy formation that the noisy, collision-rich parts of the cosmic web have long since erased. Every void galaxy is a message from a quieter time. Reading those messages clearly requires understanding the threads they're attached to. And understanding these threads requires going further into the physics of what fills the space between them. Cut a galaxy off from its neighbors for long enough, and something strange happens. It doesn't die, it doesn't freeze, it keeps going. But the path it takes, the way it ages, the stars it builds and loses, all of it diverges from the path taken by galaxies in crowded environments. A galaxy growing in isolation follows a different script entirely. Most of what we know about galaxy evolution comes from galaxies in dense environments, near clusters, along major filaments, inside groups. These galaxies experience frequent gravitational encounters. They pull gas from each other, they trigger bursts of star formation through near collisions. They occasionally merge outright, combining into larger systems. Their evolution is turbulent, shaped as much by what happens to them as by what they do on their own. A void galaxy skips all of that. Without close neighbors, there are no tidal interactions stripping gas away. Without mergers, there are no sudden starbursts consuming huge amounts of raw material in a short time. The void galaxy grows slowly and steadily, using the thin streams of gas available along its hosting filament. It doesn't burn fast. It doesn't exhaust its fuel quickly. It ages at its own pace. This extended, steady star formation has a measurable signature. Void galaxies tend to be somewhat bluer than average. meaning they are actively forming stars at a moderate rate. They haven't gone through the rapid consumption and subsequent quenching that merger-driven galaxies often experience. Their stellar populations are different, younger in some respects, simply because they haven't been pushed through the violent cycles that accelerate aging in denser environments. Some researchers describe void galaxies as cosmologically young, meaning they have experienced fewer major evolutionary events despite their age in years. The long-term endpoint of this slow evolutionary path is uncertain. Standard models of galaxy evolution, built largely from observing galaxies in dense regions, don't predict reliably what a galaxy that has avoided all major interactions for 10 billion years looks like at the end of its star-forming life. The models were not designed with extreme isolation in mind. One possibility is that void galaxies outlast their denser counterparts as active star-forming systems. While cluster galaxies are stripped of gas quenched by hot cluster environments and gradually transformed into old, red, star-poor ellipticals, a void galaxy might keep forming stars at a low but steady rate for far longer. It might still be building stars when the galaxies in a nearby cluster have gone dark. Observations of known void galaxies support some of this picture. They tend to retain more gas than expected for their age. Their star formation rates, while not spectacular, are sustained. They are not the dead galaxies that dense environments often produce. This has implications for thinking about life in the universe. A galaxy still actively forming stars billions of years into the future has more opportunities to produce planetary systems around young, long-lived stars. The isolation that seems like deprivation is also, in a sense, a form of protection. The void guards these galaxies from the violence that reshapes and eventually quiets their more social cousins. And the void does something else too. It protects measurements. The same isolation that keeps void galaxies undisturbed also keeps the space around them unusually clean for scientific observation, which leads to one of the most powerful applications of void science in modern astronomy. The cleanest place to do science is somewhere nothing gets in the way. In a typical region of the cosmic web, measuring the behavior of gravity or the properties of dark matter is extraordinarily difficult. Massive clusters pull everything. Filaments carry streams of high-energy particles. Galaxies collide and inject energy into the surrounding gas. The gravitational environment is complicated, and separating the signal you're looking for from the noise produced by everything else requires enormous effort and imperfect assumptions. Inside a cosmic void, most of that noise disappears. The interior of a large void is one of the quietest gravitational environments in the observable universe. There are no massive clusters nearby, no major filaments injecting energy. The galaxies that survive inside the void are small, isolated, and gravitationally weak by cosmic standards. The dominant physics in a void's interior is the smooth, large-scale behavior of gravity acting across enormous distances, with almost nothing in between to complicate it. This makes voids extraordinarily valuable for testing theories. Specifically, voids are ideal for testing modifications to gravity. Standard gravity and modified gravity theories like Milgromian dynamics make different predictions about how matter moves in very low density, low acceleration environments. Those differences are largest precisely where the gravitational field is weakest, which is inside voids. In the crowded parts of the cosmic web, the differences between standard and modified gravity are often too small to measure reliably. In a void, they become accessible. Researchers have proposed several specific tests. The shape of voids, whether they are perfectly spherical or distorted in particular ways, depends on the gravity theory used. The velocity of galaxies near void edges should follow different patterns under different gravity laws. The rate at which voids grow over time is another distinguishing signal. Each of these is measurable with sufficiently precise surveys. Void statistics, the distribution of void sizes, and the frequency of voids of different depths are already being used as a cosmological test. The number of large voids, how often they appear, and how deep they get are all sensitive to the underlying physics. Survey data already provides constraints. though not yet tight enough to definitively favor one gravity theory over another. The full power of voids as a laboratory for gravity testing hasn't yet been realized. Current surveys are not deep enough or wide enough to map void shapes and galaxy velocities at the precision needed for decisive tests. The next generation of surveys, covering billions of cubic light years with much greater galaxy density, will change this. Some physicists believe that void statistics will ultimately be among the most powerful probes of fundamental physics available to astronomy. They avoid the complications of the crowded cosmic web. They probe the large-scale behavior of gravity directly, and they exist everywhere across the observable universe, providing an enormous number of independent measurements that can be combined for statistical power. The void is often seen as what's left after everything interesting is drained away. The reality is the opposite. What the void is left with is a pristine environment that the crowded universe can never provide. Empty space is the clearest window into how the universe works at its most fundamental level. And the biggest window of all may be the one we are currently sitting inside. Every map has an edge. Our map of the universe extends to the edge of the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. Beyond that boundary, light hasn't arrived yet. We can't see it, we can't map it. Whatever exists out there is, for now, invisible to us. But the existence of enormous structures like the Boötes void and the KBC void raises an uncomfortable question. If structures this large can exist inside the observable universe, what might exist beyond its edge? The universe almost certainly extends far beyond what we can observe. Many cosmological models predict a universe vastly larger than the observable sphere, some by factors of millions or more. In those vast unobserved regions, the same physical processes that shaped our observable universe would have operated, forming galaxies, filaments, clusters, and voids. If voids the size of the KBC void form naturally, even rarely, in our observable region, then enormous voids should exist in the unobservable universe too. Potentially much larger ones if the universe is large enough and old enough for structures on greater scales to have formed. Whether structures larger than the KBC void exist within the observable universe is itself an open question. The Hercules Corona Borealis Great Wall, a proposed concentration of galaxy clusters spanning roughly 10 billion light-years, would be far larger than any void identified so far. If it is real at that scale, it implies the cosmic web contains structure on scales much larger than the standard model comfortably predicts. Some theoretical models suggest the universe may have a hierarchical structure that extends to arbitrarily large scales, with voids inside larger voids, like a cosmic foam with no characteristic bubble size. If this is true, the KBC void is not a unique or extreme object. It is one level in a hierarchy that continues beyond our ability to observe. Testing this idea requires mapping the universe at scales comparable to the observable universe's full extent. Current surveys cover a fraction of that volume with meaningful density. The gaps in coverage are enormous. Structures comparable to the KBC void could exist in those gaps and remain undetected with current data. What we do know is that the structures we have detected are already straining standard predictions. The KBC void, if confirmed at full size, sits at the boundary of what the standard model can accommodate. Anything larger would require new physics, modifications to the cosmological model, or a fundamental rethinking of how structure forms. The map we have shows a universe already weirder than predicted. What lies beyond the map's edge may be stranger still. This is one of the reasons cosmologists are so eager to push surveys further, deeper, and wider. Every additional billion light-years of mapped volume either confirms the standard picture or reveals something that doesn't fit. So far, the deeper the surveys go, the more they find to argue about. And some of the most precise measurements coming back from those surveys are revealing effects that even a decade ago, most physicists didn't expect to be detectable. Light changes as it travels. Passing through dense regions of the cosmic web, light gets lensed and bent by gravity. Passing through hot gas, it scatters. Passing through regions of intense magnetic fields, it shifts polarization. Every environment leaves a fingerprint on the light moving through it. Voids leave a fingerprint too, a subtle one, but measurable. When light travels through a cosmic void, it experiences what physicists call the integrated Sachs-Wolf effect. The mechanism is tied to the universe's accelerating expansion. Here is how it works. As light enters a void, it falls into a slight gravitational well. A void is underdense, meaning the gravitational potential at its center is slightly higher than outside it, and light loses a tiny amount of energy entering it, exactly as it would climbing out of any gravitational field. In a static universe, light would gain exactly that energy back when it exits the void on the other side, falling back down the potential slope. The net effect would be zero. But the universe is not static. It is expanding, and dark energy is accelerating that expansion. By the time the light exits the void has grown slightly. Its gravitational well is slightly shallower than when the light entered. The light exits a weaker well than it fell into. The result is a net energy loss. The light is very slightly redder after passing through the void than it was before. This is the integrated Sachs-Wolf effect, and it has been detected in the cosmic microwave background. By correlating the locations of large voids and superclusters with temperature patterns in the cosmic microwave background, researchers have confirmed that voids produce cool spots and dense regions produce warm spots in exactly the pattern this effect predicts. The integrated Sachs-Wolf effect is one of the clearest direct observational signatures of dark energy. The effect only exists if the universe's expansion is accelerating. In a matter-dominated universe without dark energy, the potential well would not change while light crossed it, and the net energy shift would be zero. The detection of the effect confirmed that dark energy is real and active today. Using the integrated Sachs-Wolf effect to study the KBC void directly is technically challenging. The void is enormous, and its signal would be spread across a large area of the cosmic microwave background sky. Separating its specific contribution from the contributions of many other structures along the same line of sight requires statistical methods that are still being refined. But the principle is sound. The KBC void, if real and large, should be imprinting a measurable cool spot on the cosmic microwave background sky. Finding and confirming that imprint would be direct observational evidence for the void's existence independent of galaxy counts, settling part of the ongoing debate about its size. The void leaves a mark on the oldest light in the universe, and that connection between the void around us and the ancient light crossing it hints at something even more profound about the relationship between emptiness and the fabric of space-time itself. The lambda CDM model is the most successful theory in the history of cosmology. It describes the Big Bang, the formation of the cosmic microwave background, the growth of large-scale structure, the accelerating expansion of the universe, and the distribution of matter across billions of light years. It makes predictions that have been confirmed by dozens of independent experiments using completely different methods. For decades, it has been the framework every cosmologist works within, and right now, it is under more stress than at any point in its history. The Hubble tension is the most famous crack. Two precise, independently verified measurements of the universe's expansion rate disagree at 5.3 sigma. The standard model cannot explain both simultaneously without modifications. The KBC void is another crack. A void of its proposed size and depth is a 6 sigma tension with the model's predictions. Standard physics, with dark matter and dark energy as currently modeled, does not produce structures like it within the age of the universe. Large-scale anomalies like the Hercules Corona Borealis Great Wall, if confirmed, represent additional stress. Structure on scales of 10 billion light years is incompatible with the cosmological principle, which the lambda CDM model depends on. There are 3 broad responses to this accumulation of tensions. The first is to argue that the measurements are subtly wrong, that systematic errors in the Hubble tension distance ladder, or incomplete surveys of the KBC void's extent, or confirmation bias in the detection of large-scale structures, are producing apparent anomalies that will dissolve as measurement precision improves. The second response is to patch the standard model. Add an ingredient, modify dark energy to evolve over time. Introduce a brief period of early dark energy that changes the pre-recombination expansion rate. Adjust how dark matter behaves on large scales Each patch is designed to resolve one tension without breaking the things the model already explains well. The third response is to consider whether the foundations need replacing, whether the cosmological principle is wrong, whether gravity behaves differently than general relativity predicts at cosmological scales, whether dark matter and dark energy are approximations of something more complex. No consensus has formed around any of these responses. The measurements keep coming in, some support the standard model with refinements, others deepen the tensions. The scientific community is genuinely divided about whether the resolution will be a small adjustment or a major overhaul. What is clear is that the lambda CDM model, extraordinary as it is not the final word. The universe has been returning data that doesn't perfectly fit for long enough that the anomalies can no longer be dismissed as noise. The voids are where the noise is loudest. The KBC void in particular sits at the intersection of every major tension in modern cosmology. It touches the Hubble tension, the cosmological principle, the behavior of gravity at large scales, and the statistical predictions of the standard model, all at once. Resolving what the void actually is, how large and how deep, will go a long way toward resolving whether the standard model needs a patch or a replacement. The telescopes being built right now may provide that resolution within a decade. Imagine a different Earth, same planet, same sun, same blue sky and familiar seasons. But the Milky Way is inside the Boötis void instead of the cosmic web. The night sky looks the same in all the ways that matter close to home. The moon, the planets, the familiar constellations made of nearby stars. But zoom out and everything is different. From inside the Boötis void, the nearest significant galaxy cluster would be hundreds of millions of light years further away than it is from our actual location. The faint smudges of the Andromeda Galaxy and the Magellanic Clouds, visible to the naked eye from Earth, would still be there, since they are nearby companions of the Milky Way. But beyond those immediate neighbors, the sky would go dark in a way it does not from our current position. Astronomers built giant telescopes in the 20th century, partly because they suspected other galaxies existed beyond the Milky Way. The first conclusive evidence came in the 1920s, when Edwin Hubble measured the distance to a galaxy called the Andromeda Nebula and showed it was far outside our own galaxy. From inside the Boötis void, even Hubble's most powerful instruments would have struggled to detect the next galaxies beyond the local group. They would have been so faint, so distant, that the technology of the 1920s couldn't have reached them. A civilization inside the Boötis void might have concluded, based on centuries of astronomical observation, that the Milky Way was the entire universe. No other major structures visible. No evidence of the cosmic web. No way to map the large-scale structure of reality, because the nearest large-scale structure would be too far away to see. Science develops from what can be observed. A civilization, with no visible neighbors, might develop a completely different cosmology, one in which the universe is small, isolated, and singular. Whether that hypothetical civilization would eventually find indirect evidence for a larger universe through the cosmic microwave background, through redshift measurements of very faint objects, through the gravitational effects of distant matter on light, is an open question. The evidence would be there. Detecting it without knowing where to look would be another matter. Our actual location in the cosmic web, relatively close to the edge of the KBC void, rather than at the center of the Boötis void, gives us access to nearby galaxy clusters and filaments. The Virgo cluster, one of the nearest major concentrations of galaxies, sits roughly 54 million light-years away. The Perseus cluster is about 240 million light-years out. These nearby structures were critical for building our understanding of the universe's large-scale architecture. We got lucky with our address. Not perfectly lucky, we are inside a large, underdense region, which skews our measurements, but lucky enough to see beyond our immediate neighborhood and piece together the structure of the cosmic web. A civilization inside the Boötis void might never have gotten that far, and this thought experiment carries a real lesson for science done from any location. What you can see depends on where you stand. What you cannot see shapes the theories you build. The universe is far bigger than any one vantage point can reveal. The debate about the KBC void won't last forever. New instruments are coming. Surveys are being planned and built that will map the distribution of galaxies across billions of light years with a level of detail current telescopes cannot match. When that data arrives, many of the open questions in the story will have answers. Some will close, others will open wider. The Vera C. Rubin Observatory in Chile began scientific operations in 2025. Its primary instrument, a camera with an imaging sensor the size of a small car, will photograph the entire southern sky repeatedly over a 10-year survey program. By the end of that program, it will have catalogued tens of billions of galaxies and stars, mapping their positions, distances, and properties in unprecedented detail. For the KBC void specifically, the Rubin Observatory's galaxy survey will dramatically improve measurements of galaxy density across the distances where the void's boundaries are currently debated. If the void truly extends 2 billion light-years, the new data will show it clearly. If it fades out at shorter distances, the data will show that too. The ambiguity in the void's size, which has fueled debate since 2013, will shrink significantly. The Euclid Space Telescope, launched in 2023, is conducting a wide-field survey of galaxies across more than 1/3 of the sky, reaching distances of roughly 10 billion light-years. Euclid is specifically designed to measure baryon acoustic oscillations and the growth of large-scale structure with high precision, making it directly relevant to testing the cosmological models that the KBC void challenges. Together, the Rubin Observatory and Euclid will provide overlapping, complementary datasets covering much of the sky at depths far beyond current surveys. Cosmologists will be able to test the KBC void's properties from multiple angles, using multiple methods with datasets large enough to reduce statistical uncertainties to very small levels. What those surveys might find beyond the KBC void is genuinely unknown. The current map of the universe, at distances beyond a few billion light-years, is sparse. Large structures may exist in that uncharted volume that are as surprising as the KBC void was when first proposed. The surveys will either confirm the standard picture at large scales or reveal new anomalies that push physics further into uncharted territory. Future radio telescope arrays, including the square-kilometre array being built across Australia and South Africa, will complement optical surveys by mapping the distribution of hydrogen gas across cosmic distances. Hydrogen traces the cosmic web, even in regions where galaxy surveys are incomplete. The combination of optical and radio data will give scientists a three-dimensional picture of the cosmic web at a resolution never previously achieved. The next decade of astronomical observation is likely to be the most scientifically productive in the history of cosmology. The instruments exist. The questions are defined. The data is coming. Whether the answers confirm that the standard model needs only small adjustments, or reveal that the foundations of cosmology need serious rethinking, will depend on what those instruments find when they look into the void, and into the structures beyond it, stretching across distances that current maps have barely scratched. For most of human history, we thought we were at the center of everything. The sun circled the Earth, the stars circled the sun. The universe existed to frame us. Each time science pushed back on that assumption, the demotion stung. The Earth is a planet among 8. The sun is a star among hundreds of billions. The Milky Way is a galaxy among hundreds of billions more. And now this. The Milky Way sits near the center of one of the largest underdense regions ever identified in the observable universe. A void 2 billion light-years across, with 30% less matter than the cosmic average, surrounding us in every direction. Our cosmic address is not in the bright, crowded part of the universe. It is in a hole. That hole has been quietly affecting our measurements for decades. Every calculation of the local expansion rate, every survey of nearby galaxies, every measurement that depends on the gravitational environment around us, all of it filtered through the KBC void, all of it subtly colored by the fact that we live in an underdense region of space. This is not a small thing. The Hubble tension, one of modern physics' most stubborn problems, may be at least partly a consequence of our location. The 6 sigma conflict between the KBC void and the standard model may signal that the foundational assumptions of cosmology need revision. The modified gravity theories being proposed to explain void growth may rewrite how we understand the force that built everything in the universe. Some physicists argue we are at a turning point comparable to the Copernican revolution, the moment when science accepted that the Earth was not the center of the solar system. That revolution required abandoning a cherished assumption. The current situation may require something similar, abandoning the assumption that the cosmological principle holds perfectly at all scales, or that our current theory of gravity is complete. Whether the resolution will come from new data confirming the void's full extent, from theoretical breakthroughs in modified gravity, from revised models of dark energy, or from something nobody has proposed yet, is genuinely unknown. The pieces are moving. The picture is changing. Science is doing what it does when observations and models collide, arguing, testing, and slowly converging on something closer to the truth. What is certain is this: the universe is stranger than we thought before 1981, when Kirshner's team stared at a stretch of sky and found almost nothing where everything should have been. Stranger than we thought in 2013, when 3 astronomers suggested we might be living inside an enormous hole. And stranger still with every new survey that returns data from deeper in the dark. The void is not an absence of meaning. It is the universe's most extreme environment, a natural laboratory, a measurement challenge, a fundamental test of physics, and a reminder that location shapes everything, including what we think we know. We live in a hole in the universe. The hole has a shape, it has a history, it has consequences that reach into every corner of modern cosmology, and we are only beginning to understand it.